So now we're starting the bootstrap and matrix models and lattice Yang-Mills theory discussion section. So first Martin will talk for 10 minutes and then Volodya will talk for 10 minutes. And then we'll open the floor to discussion. So Martin.
Okay, so if you don't hear me, please wave or do something. Okay, so thank you for the intro. Okay, so in the part one, I'm going to talk about loop equations and bootstrap methods in lattice gauge theories, and this is based on a paper I wrote with my student Peter Anderson a while ago, and at that time we were hoping that some smarter people could make good use of these ideas, and Volodya is going to talk about that after this. So the motivation is similar to what John was saying, is if can one define gauge theory purely in terms of gauge invariant quantities, and ADS-FT gives a possibility by using string theory, but the more direct approach is to use Wilson loop and the loop equation of Migdal and Marchenko, as he also mentioned. And I'm going to concentrate in lattice gauge theory because that's you avoid the normalization problems, and also it's easier to understand the loop equation. And I'm going to work in the Large N limit. So consider a cubic lattice, as was already discussed, and this is in any dimension. And at each link there is a SUN matrix, and one can define a plaquette like a product of these four matrices at taking the trace, and you sum overall plaquettes, and with different orientations you get the action. So as also John said, you can write the action as a sum of small Wilson loops. And then you can take other larger Wilson loop by multiplying the matrices associated with the links. If the link goes backward, it's a dagger. And the expectation value of the Wilson loop is just a normal integral with many, many dimensions. So in principle, in lattice, you use Monte Carlo to evaluate. In the Large N limit, the relevant coupling is the Toft coupling. Acts like a temperature, so small coupling is small temperature, and you are interested in low energy configurations, and large coupling is large temperature, which corresponds to large entropy. The loop equation of Migdal and Marchenko is based on the action. So the action here is a set of small Wilson loops that acts on the Wilson loop and acts in the following way. If there is a link in the Wilson loop, we look at all the Wilson loops in the action that share a link, for example, this plaquette, and then we connect the plaquette with the two possible orientations. So in one orientation, they cancel, and you get a minus, and in the other, you get an extra curly loop like that. And then there is a self-intersection term. Self-intersection here means going through the same link, not the same vertex. And if you go through the same link parallel, this Wilson loop splits in two. And if it's opposite, but it's also split in two, but with a minus sign. And so this sigma is plus or minus. And the loop equation that follows from the action, from doing the variation of the action, is this. And here I'm using the Large N limit. In the sense here, I should have the expectation value of the two Wilson loops, but that's a product of the expectation values in the Large N limit. One can write this loop equation also as a matrix and acting on a list of Wilson loops, plus this is a self-intersection, and one term here, I put it on the right for simplicity. And one can get this idea of using the loop equation, the Large N limit is like a classical limit, so this should be the classical equations of the action that John was talking about. So one makes a list of Wilson loops. These are like in 3 dimensions, but you just list Wilson loop 1, 2, 3, 4. And then you get some equations. And the question is, can we compute the Wilson loops just by solving these equations without any reference to the variables u? One faces a problem because to properly define mathematically this problem, we have to cut the number of Wilson loops up to some length L and then take L to infinity. But if we have Wilson loops up to length L, we have one equation of motion for each of them. But they involve Wilson loops of length L plus 4 because you add the curve. And that means that you have more variables than equations, and it's highly undetermined, and you have infinite number of solutions. So this limit L goes to infinity is not well defined. One thing you can do is to set these larger loops that you don't know to 0, but that's only true good at strong coupling. And the method we propose is to, instead of setting those to 0, you let them free. And then we use a set of positivity constraints to put bounds on the expectation value, and this gives a well-defined limit and L goes to infinity, and we think that's the appropriate way to work with the loop equation. So what are the positivity constraints? You get 2 points of the lattice, and you get a set of open loops going from one to the other. And then for each of these loops and a given configuration, you get the matrix associated with the open loop, and you make arbitrary linear combination with these any coefficients. And since the trace of A dagger A is positive for any matrix A, this thing is positive, but this trace is just the closed Wilson loop obtained by going along path L prime and then coming back along path L. And the expectation value of something positive is always positive. And since this is true for all coefficients, we get that the matrix constructed in this way with entries equal to Wilson loops, closed Wilson loops, is always positive definite. And divided by the number of loops that I have here, the trace of this matrix is 1. So it's like a density matrix. And it is the entropy associated with this density matrix measures the information we lose when we trace over the color indices to construct it. And indeed, it behaves like the entropy of the system, because if I evaluate this in the same lattice simulation at small temperature, a small capping, the entropy is 0. And here I'm taking different rows by different initial and final points. And at large temperature, it's set to raise to 1. And you can see a phase transition here. And another interesting point is that the space of allowed row matrices ends when one eigenvalue becomes 0. But when one eigenvalue becomes 0, one can see that this means that the linear combination of the Wilson loops is 0, the open Wilson lines. And that means that by closing it with any other arbitrary line, you get an infinite number of constraints on the Wilson loop. So these theories that give us the boundary of the space of allowed space of row matrices are very special. And if we apply this case to the two-dimensional case, and that's just the unitary matrix model as shown by Gross, Witten, and Vadia, the exact solution is known, is this dashed line. By just putting a very few Wilson loops, you bracket the minimum and the maximum, you bracket the expectation value of the plaquette, or the mean energy of the lattice as a function of the top capping. And you can put more Wilson loop because it is just one plaquette, so that will just go on top. But you can do a three-dimensional case. This is where Boloya had a very big improvements, as he's going to describe. But in our case, we have this red dot, which is a numerical lattice simulation that we did. It's very standard, so nothing there. Unusual, and these are like the weak and strong capping expansions that people know. But this is a bootstrap method where you bracket the solutions. It's not perfect, but we see that, well, you obviously bracket the solution as we promised. And there is this interesting thing that at weak coupling, you match the upper bound, and at strong coupling, you match the lower bound. And the continuum and the upper bound, well, okay, let me just show the four-dimensional case where you have the same thing. But the continuum limit is when lambda goes to 0, because the lattice is the smallest scale you have, and the theory is asymptotically free, so lambda should be very small. And there, the actual numerical lattice simulation seems to match the upper bound. That means that you have this infinite number of constraints on the Wilson loops, and we hope that is useful for the continuum limit. And finally, I want to mention something we didn't publish yet, which is a connection with the gradient flow. So gradient flow is a method to have a lattice configuration and smooth it out. And when people in the lattice community compute large Wilson loops, they compute it in the smooth out lattice, because in the usual lattice that we are talking about, the fluctuations are too big, too much noise. And the way to flow the lattice or smooth it out is to solve equations for the evolution equations for the matrices in the links. But we check that if you flow the Wilson loops using the same thing, they just flow with the same operator that appears in the loop equation. So you just do some exponential acting on the Wilson loops, and you get the flowed Wilson loops. But one thing we can check is that the flowed Wilson loops, if you put them in the same matrix row, should still be positive definite, which will be giving us an infinite number of new positivity constraints. However, we don't know if these positivity constraints are new or are included in the previous constraints. So to summarize, we constructed this matrix rho that should be positive definite. The entries are expectation values of the Wilson loops, and this positivity highly constrains the solution of the loop equation. And we think, in fact, that is just, if you do it properly, you just get the actual solution, which is physically relevant. And this is more important in the weak coupling phase. And there, the rho saturates the bounds and has zero eigenvalues. So number increases, we check, and lambda goes to zero. And we hope that's relevant for the continuum limit. And also allows us to define an off-shell Wilson loop entropy. By off-shell, I mean that as long as it's positive definite, we don't need to put the W's expectation values from the lattice. We can put any W. And with that, we can do it. We can use it to define some free energy, for example, for the system. Okay, so that's what I want to say. So I'm going to cede the floor to Volodya.
Volodya, are you ready?
Yes, I am sharing the screen. I am taking over our discussion. Let me start from the general comment that in spite of great success of Monte Carlo, I feel it's sort of intellectually and practically an unsatisfactory situation that we have only one systematic non-perturbative method in quantum field theory to do computations. And Bootstrap emerges as a new hope. It's a more analytic approach, already with a lot of success in CFT Bootstrap and S-matrix Bootstrap. But here I will speak, I will continue Martin's talk and speak about matrix and Young-Niels theory Bootstrap. It combines word identities and positivity of correlation matrix, and has a lot of space of improvement, which we tried to introduce with my student Zhechuan Zheng for these problems, and I will explain these new ingredients: relaxation, reflection, positivity, symmetry reductions, etc., which greatly improve the efficiency. Now, let me start from the two-matrix model, which is a continuation of nice ideas of Henry Lin in matrix model Bootstrap. And we studied in this paper a model which is unsolvable by any analytic methods, which it's a two-matrix model with commutator square interaction and two quartic potentials for each matrix. And the main quantities we'll study correspond to words, the matrix products of A and B in various combinations. The word identities, the analog of loop equations, are constructed by taking a derivative under the trace of the word and of the action, where this derivative can be with respect to A and B, and we end up with the equations on the moments for the traces, average traces of these different words, which has schematically this form very similar to what Martin presented in the gauge theory. In the right hand side we have a nonlinear term due to large N factorization. In the left hand side we have derivative of action under the trace, which gives a combination of words of slightly bigger length than the original one. And of course, in Bootstrap, we simply limit ourselves with the length of words, certain length of words, L. It gives many more words than equations, many more moments than equations, and we have to impose some conditions. Here, the Bootstrap scheme comes into the game. We have to impose the positivity conditions, namely. So we have loop equations relating all these moments, and first we form an operator, a matrix operator, which is a linear combination with arbitrary coefficients alpha of all these words, matrix words, Then we take trace O dagger O of this combination, which is by definition positive, and it defines a positive definite matrix WL, the so-called correlation matrix. So our condition is to impose all this positivity of correlations. This can be now the bootstrap process can be presented in the following form. We should minimize some physical quantity, minimize and maximize, find margins, and with respect to all these momenta, the variables, and they are subject to nonlinear loop equations with this nonlinear term, and then we impose the positivity of correlation matrix. Of course, the nonlinearity brings many complications. It's a non-convex problem of minimization, and all the existing algorithms are quite inefficient here. So we then proposed with ZH1 a crucial improvement, which is the relaxation for Bootstrap. Namely, we consider now the product of these two variables, two moment variables in the equations as a new variable xkj, and consider them as independent variables so that the equations become linear. But then we impose, instead of, we relax this equality to inequality in terms of this matrix positive definiteness, that the matrix X defined here is okay, this combination is positive definite. Equivalently, it can be written in matrix form due to Schur complement, and it looks very much like a positivity condition for correlation matrix. So we just add it to our set of conditions, hoping that for very big L's, when the cutoff increases, it boils down to the equality. And so this is already a convex problem, much more efficient for the existing numerical SDP solvers. And we apply it to our two-matrix model. Now a few results. For example, here we have the results for generic values of two couplings of the model for various lengths, cutoff lengths. We go up to L22. It's a typical island structure, and the island quickly becomes so small that we only can put a cross somewhere here on the picture. And the results are with 6-digit precision for these two moments. I forgot to say it's just two moments, trace A square and trace A4. These are exact equalities, unlike the Monte Carlo, which gives the statistical error. These are exact equalities. Increasing cutoff, we can only improve them. Here are some data. We have 95 variables at the end after exclusion with loop equations, and the sizes of the matrices are given here. Okay, that's maybe not so important, but this result took 40 hours of CPU time of the usual laptop, but it can be greatly improved. I think ZH1 promises like 2 more digits of precision, which is, of course, a very good precision for this functional integral. Work at infinite n limit, of course, it's a functional integral. So Rogov and Ya tried Monte Carlo on the same model with the results like he got 4 digits with 85 hours of work on laptop. So you see already on this problem, Bootstrap can compete with Monte Carlo efficiently. Okay, now bootstrapping Young Mills quickly, because it's unpublished work on me and ZH1 Zeng, hopefully soon published. It's a follow-up of the pioneering paper of Martin and Anderson. I pass the introduction because it's precisely what Martin explained. The loop equations, then the positivity condition on the path going from point 0 to point X. We actually, in our best chance we used x equals 0. So those are the paths starting and ending on the same point, which appears to be the most efficient. And so the results seem to be very encouraging. A few new features of our Bootstrap. So we use the same loop equations, but we, for example, we add up many equations obtained by backtracking from the contour, which doesn't change the contour, and applying the loop, the mechanical-Migdal operator to the endpoint link. So these equations appear to be very important, and they improve a lot the result. Then the relaxation trick is the same. We replace the nonlinear equations by linear inequalities, like in two-matrix model. And also we use a lot the lattice symmetry. It's a new ingredient. Because we have the symmetries, we can block diagonalize the correlation matrix, reducing enormously the amount of work for the SDP solver. Then we use the reflection positivity condition. It's a new condition in addition to positivity of correlation matrix, which uses the fact that the action, Wilson action, is symmetric with respect to, for example, reflection over the line. And there is a side link and diagonal positivity condition. So upstairs there is a original contour, and downstairs the reflected contour everywhere. Then we do the same. We sum up with arbitrary coefficients all these contours lying on one side of this line and imposing the positivity. And of course, symmetry also is used to block these reflection positivity matrices. And now the results. So this is the result for two-dimensional theory, which Martin showed. They used the this result is for the full two-dimensional theory, which is a much more complicated calculation than one plaquette calculation shown by Martin. But we needed it to see how good we can approximate the exact result here by dotted line. Okay, this is 2 dimensions. Now our best results correspond to 3 dimensions. The Monte Carlo data we took from Martin's paper, it's at n equals 10 and c equals n. Then I showed a few days ago the L equals 12 upper and lower limits. And now just a very fresh result. These dotted lines give the upper and lower limits for L equals 16, then the length of loops equals 16. And you see a huge improvement. It's indeed huge, especially it's important for weak coupling. Here are some data how we reduce the matrices, but it's okay. The table shows how the plaquette average U max, for example, in the weak coupling regime is improved with respect to Martin's results. Although we have a smaller length, we have many more conditions on positivity conditions on and loop equations. And so all this comparison shows that the results are quite encouraging. Okay, and this is the 4-dimensional plot for L equals 12, but the computer is working on L equals 16, and hopefully it can go up to from the estimations of Zhechuan, maybe up to 20, maybe 24. So this should be really a great improvement. Okay, then I show just the flash with the literature. Maybe you can see it later in the on the website of all the papers I found on this subject. Hopefully some people are present in the audience, and we will continue with the discussion here. These are our common questions with Martin, which we invented for this discussion. So please go on with the discussion. Thank you for your attention. And
okay, so we'll open up the floor. So we'll start with Marat.
Yes. Can you hear me okay?
Yep.
Okay, so the question has to do with the next step, which, let's say you wanted to calculate some correlation functions of some two local operators. In large N, such a thing will factorize. So how do you deal with the factorization of such local operators?
Sure.
And really want the correlation?
I may answer the question, maybe.
Yes, please.
Also will comment. Of course, if it's finite n, it's a very difficult problem for Bootstrap, because if you put your loops on very big distance, you have to essentially to add this distance to the length of the loops, and it may be difficult. But on the other hand, it's possible if we limit by a certain length between these operators. And what is nice in 1 over n expand, so we have to go to the next limit, to the next order, 1 over n, because two-loop correlator, say global correlator, is already, due to the factorization, we have to go to the next order to correlate them. And actually, you can write loop equations for such two-loop quantities. And what is nice, they're all linear. So all the 1 over n orders are linear problem once you solve this basic nonlinear problem of mechanical equations. So it could improve the situation. But of course, it's for the future.
No, I just want to mention that feel free to make any comments or say whatever you want, because it's a discussion session, so or answer the questions.
Yeah, let me also encourage you, if you want to break in, just wave your, with the, if we're on the same topic, if you want to break in, just wave your hands. Raise your hand so you go to the top, but also wave your hand so I can see it. Okay, so anyway, Shota.
Okay, so I wanted to ask a question about the Lucius gradient flow to Martin. So, because it was a bit too quick, so you're basically saying that the flow-Wilson loop operator also satisfies the same kind of like positivity condition?
Yeah, that's because what you do, you flow the links to get a new configuration, which is smoother, right, but the links are still unitary. So if you compute the Wilson loops in the flow lattice, they are also they have the same constraint, because the configuration is not the one that most appears, if you want, in the Monte Carlo, but it's a valid configuration with unitary matrices, and so the positivity constraint should be true.
I see. Then the main difficulty will be relating the flowed operators and unflowed operators, because typically they are kind of quite complicated, I guess.
Well, it's done with the, the main difficulty is that Peter graduated.
Okay. But I feel like the relation between the unflowed and flowed operators are typically a little bit complicated.
Well, it's E minus T, the loop Laplacian, as people call it, applied to the Wilson loop. So it's a differential equation. You have to solve in T, like a Schrödinger equation. Right. So dt Wilson loop is a K applied to Wilson loop. But it's not particularly difficult, I think.
Okay. And have you tried the same for the matrix model? Does it work for the matrix model?
I don't know. I don't know what happens now.
I see. Thanks.
I was initially trying for the lattice simulation, trying to do the flow and first check that everything was fine. But okay, at some point I was doing something else. But yeah, I'm interested in doing that.
Yeah, that's an interesting idea. Yeah, thanks.
Also, that's, as I said, the flow method is how lattice people compute the Wilson loops in practice. So for large Wilson loop, the main problem here is when lambda goes to 0, we have small loops. You have small loops, and you actually want to prove that the big loops obey area law. So that's the main problem. And the big loops in lattice are computing the flow lattice, so might be useful.
Okay, Lance.
Hey, thanks for this very interesting discussion. It's great to see this approach being revived. I was actually around Princeton when Larry Yaffe was working on the classical limit, and he was able, I mean, they attempted to actually get out things like Lubal spectra by using the classical nature to construct a classical energy as a function of the loops and identify the quadratic behavior in different directions to try to read off masses. Of course, they had the computing power of the 80s, which is probably a lot less than the laptop you have right now. So I'm just curious if you guys have thought about, how to do this for glue ball masses. Are there other things that crop up when you try to address that and so on?
I mean, if I can say, in lattice, people compute glue ball masses by putting correlations of two Wilson loops, as was mentioned. And we don't know how to do that. Yeah,
but that's not how Larry did it. He minimized a classical energy functional in some way, and then identify the quadratic behavior. And but I don't know how that would play with incorporating these positivity constraints, which I don't know that he did.
I mean, I have his paper here, but if you want, I could share it. If I can share. Yeah, I cannot share my screen.
Anyway, we could discuss it later, I guess.
Can you provide the link in the chat?
I can find it.
Okay.
Yeah, it's called Large N Limits as Classical Mechanics.
Well, that was just the first paper, and then they did some more concrete things later on. In fact, Joe was there at the same time, actually.
Was I?
Yeah.
Well, I thought he was doing that slightly after I left, and when you came.
Do you remember Frank Brown?
Okay, yeah, I
Tom Dickens.
Frank,
He was, and Bill Somsky. Anyway,
I remember all this.
They were the students on the. Yeah.
It's using large and coherent state bases.
Coherent states, yeah, that's an important thing.
Large and coherent state, and then you can show that the quantum fluctuations are suppressed by 1 over n, and he does work in the Hamiltonian formulation. He does some truncation on the Hilbert space, but at the time, because of the computing power, I don't think practically it was a very
So Midhat, do you know of anybody else who tried something similar later?
No, not recently.
Yeah.
It is only used, this approach is only used to prove this idea of large and orbifold and orientfold equivalences.
Okay.
For the equivalence of super Yang-Nielsen QCD with symmetric and anti-symmetric. It is not used as a computational tool recently in the last 15, 20 years, as far as I know.
Yeah, I wasn't aware either, but I don't follow this as much. Here's in the chat, I put the reference to paper 2, and you can find paper.
Oh, thank you. Yeah. Yevitsky has some work on the old days also on this collective.
It'd be interesting to see if anything from that could be improved with these positivity constraints, too.
Yeah, Anto was working on this recently, right? I mean,
Anto Yevitsky?
Yeah, he worked in the old days and he came,
Okay.
Yeah.
No, he was interested in our paper and we discussed and he told me the old work and it was very interesting.
Yeah, I think this classical approach, they develop it in this recent paper of Antal with Domeloko.
Okay.
So that's also an interesting development, but not yet. We still have to wait for great numerics there, I would say. But
so is that the paper, Large N Optimization of Multi-Matrix Systems?
Yes, I think it's something like that. They're using this idea that there are classical variables and they apply the master field idea. In fact, that's your matrices become classical objects. In principle, at large N, you can find the set of matrices, like two matrix model, two matrices, which just is enough to compute traces of corresponding words, and this will be already the exact result at the large N limit. But so that could be also a basis for interesting approximations, but the problem is terribly nonlinear. I wanted also to comment on calculation of masses. So I already answered the first question, for global masses, one has to calculate the loop-loop correlator, and the problem is linear in the next 1 over n approximations. This is one direction, but also maybe since we have the full set of loops, of loop correlators, not correlators, but Wilson loop averages up to a certain length, so it's a huge information about the system. We can try to compute the meson masses by putting by summing up our paths, because we have all loops, with spinorial weights, corresponding spinorial weights on the lattice. So this is much more feasible in this situation, because you don't have to go to the next order in 1 over n. Already in the main order you would have some results. This is something which we are thinking about.
Do you mean mesons with massless quarks?
Massless or massive, you just put corresponding factors along the paths. Yeah, you just pinpoint the path at the point 0 and x, and you sum up over all loops with spinorial factors. It could be also massive.
Don't you need to enlarge the phase space to include lines that begin and end at fermion positions, and not just have closed loops? If that would be the analog of dynamical fermions on the lattice, I would have thought.
Dynamical, of course, it's difficult to start with. Dynamical.
So you would do a kind of analog of a quench calculation.
Yeah.
Right?
Like Hopf calculated it in 2 dimensions. Here we can do it in, say, 3 or 4 dimensions, but just summing up our loops, because we computed all of them with certain precision.
But I think it would be like a quenched calculation on the lattice, if I understand you correctly.
Large N, it is quenched.
Oh, okay.
Yeah, I mean, these.
So you say it's
fermions
just suppressed because of large N fermion loops.
Yes, but
as long as you have a fixed number of fermions. In the real world, NF is close to NC, so.
Of course.
Pedro, you had your hand up before, or are you still?
Yeah, no, probably it's a bit too technical, but I have a question. So in this 1 over n corrections, which you say are linear, the coefficient of this linear system are the solutions to these equations that you are solving, right?
Sure. Mm-hmm.
But if I just take this 1 over n correction equations that are linear, is the compatibility of these equations, would it automatically imply the equations that you solved? Are they some kind of Lax pair for this leading order, or no?
There is no integrability, so I wouldn't apply this terminology. But of course, the kernel which you have to invert includes your 0 order approximation, the solution of McCain-Migdal equation. You don't have to correct it. In the next order, you simply define the kernel, and all these equations are known, of course, and you invert this kernel. It might be also not a simple problem, but at least it's linear. You don't have to apply the bootstrap. You just.
So tell me if I'm thinking correctly. Can I think that these leading order in n equations are describing the vibration of the string, right?
Yes.
But with a fixed boundary, and then I attach these vibrations of string into these correlation 2-point functions, for example, because the same vibrations are there also in the cylinder and so on.
That's true. That's true.
But then, if I did not know what was the microscopic model that led to these loop equations. If I want to bootstrap, but also not even knowing what theory I'm bootstrapping, and I just want to put any consistent zeroth order result that will describe these fluctuations, could I imagine that I would be agnostic about the leading order and try to solve the equations to subleading order and bootstrap both at the same time?
That I'm not sure, because we start, of course, from very precise Wilson action, but say I would turn it differently. I've drawn here a picture of maybe application to Flux Tube bootstrap. Then you don't know at least the ground state. You want to bootstrap the ground state. Maybe applying the loop, this bootstrap idea, you can bootstrap the ground state. Maybe it's somewhat similar to what you propose, that you write, for example, a loop equation ad hoc, maybe reminding Young-Mills equation by different with some parameters, and you try to bootstrap it and see. Say it's sort of. It reminds me this problem, because you start off from the equation where you don't know the vacuum, so you start from some more of unknown quantities.
And in this approach, the one we are using now, the 1 over n appears only in the self-intersection term, so it will be the product plus a little bit. And so in the way you are doing it, you will have the difference between this x minus the product, not equal 0, but equal to the 1 over n, right? And maybe you can put bounds on this extra thing.
Mm-hmm.
Actually, I have a question. So to either one. So in the d equal 4 case, where you have this first order phase transition, so is this first of all, is this a correct statement that the lower bound would always be a smooth function, even if you could go to L equals infinity, and the upper bound will also be a smooth function, so the two would never meet?
No, I don't think there is. When you have.
You are muted.
Well, I was making some comments before. But suppose you have like a cube and you put it on a vertex, and I say, what's the highest point? The maximum is not a continuous function, because you can change one phase to the other. So it's not necessarily continuous. So you can have kinks in the curve.
Okay, so you would actually expect that you would actually be able to see the first order phase transition yourself.
So there should be sort of a hysteresis, yes, phenomenon, like you can.
Okay, so it's not like they'll never meet, and then you have to jump. You have to make a jump on your own somewhere without actually knowing where the jump is.
Sorry, I made a comment before, so I guess I was muted. Can I make it again?
Yeah, okay.
No, it was about the 1 over n, so I guess nobody heard it. So no, I was talking to Volodya that the 1 over n correction appears in the loop equation in the self-intersection term. So in your approach, you have this xij minus wi wj equals 0, but instead of being equal 0, should be equal to the 1 over n part of the correlation, and you may be able to put bounds on this correlation. That was my comment. Sorry.
Wait, but you can just write equation on. You speak about the two-loop correlator, yes?
Yes, because it appears in the self-intersection term.
No, you can generate the equation where already it doesn't contain n. I mean, for example, if you look up the old review of Sasha Migdal, you'll see how to generate these next equations, and you see that it's a linear equation with forcing term. Both forcing term and kernel contain the solution of zero order McCain-Migdal equation, but nevertheless it's linear and it doesn't contain any n already.
Okay. So yeah, we can go back to what Joe was saying.
the question of Joe.
All I'm saying is it wasn't, you know, in everything, in all of your plots, it wasn't immediately obvious that you know, that they would ever, you know, in the d=4 case, that they would actually meet. And so in the first order phase transition, there's actually a jump from the lower one to the upper one.
I mean, it could be the same as in thermodynamics. So you have one minimum, and then suddenly you figure out there is another minimum, and you jump. So that's what happens. So it's not obvious that it's not discontinuous.
Well, first of all, in this approach, of course, you will never find this hysteresis. It will be always a smooth curve, more and more, of course, steep, but smooth curve. And in principle, both the lower and the upper limits will approach to this single curve.
Okay.
It doesn't look like they approach at the same rate, by the way. It always looks like the maximum is doing better than the minimum to me. If you show some of those plots again.
Yeah.
There is a reason.
It's doing better at weak coupling, but the minimum is doing better at strong coupling, I believe.
Yeah, but I thought overall maximum was better if you had to pick one of the two curves.
Yes.
Do you want to show those, Volodya? If you have
There is
the slide or two?
Yes.
Yeah, it's towards the end.
Just a second. This is 4-dimensional.
Well, that one isn't so dramatic.
Yeah, better 3-dimensional.
Okay, that one doesn't agree with my theory, so throw it out.
But that's 3 dimensions, so there's no phase transition. So that one.
There is.
There is. Third order.
Oh, there is? Okay, but it's very, okay.
It's third order transition according to numerics.
Yeah, but the 4 one is more.
Anyway, for this one, max looks better than min. Maybe not in 4 dimensions.
And there is a reason for it. And maybe there is a reason for it, which say maybe Zhechuan, my collaborator, can say it because he explained me very well why it is. Zhechuan, are you here?
Sure, I'm here.
Okay. Can you comment on this? Why the upper limit is much better in weak coupling, and why in the strong coupling it goes in the middle?
I mean, there is a very general comment about it. That is, through the loop equation and the positivity conditions under a certain cutoff, we have actually allowed the region of finite volume. So the question is, in this finite volume, which point is all the solutions in this finite volume, they all satisfy all the loop equations and the positivity conditions. We are asking why which point is expected to be closest to the exact solution. My answer is it should minimize some kind of effective action. The effective action, you can think it as doing an integral, the change of variable in the integration from the matrix element to the invariant Wilson loops. So under the effective action will become some minus s plus some lowering of Jacobian. So in the weak coupling case, when the lambda is small, it's apparent that the energy part, that is the original S, it is dominant. So we expect that the exact solution very close to the upper bound. But in the strong coupling case, we expect that the Jacobian part, or the if you like, you call it entropy part, it dominates. So that we demand that we are as deep as we can into the allowed region. So we expect that it is something like maximize the smallest eigenvalue of the positivity condition. So that's why the exact value should be located likely in the middle of the 2 curves. That's my explanation.
John, and it's very striking here. It's precisely this picture. Strong coupling is in the middle of this corridor, and weak coupling maximizes, which is probably a minimization of certain action.
Yes, we have already seen it in the actually in the two matrix model. It appear already that in some region that the exact solution is in the almost in the middle of the allowed region, but in some region the exact solution is very close to the minimization of the energy. Yeah.
Okay. Shota, you want to have another question?
Yeah, I just wanted to make some like a trivial comment about the question that were raised. I think it's, yeah, at least in the matrix model, you can also write down the positivity condition involving double trace operators and design it in such a way that you subtract the disconnected piece. So I think the question to Pedro's question, so answer to the Pedro's question is yes, I think you can write down like some positivity condition that directly like proves the correlation, and probably combining it with the loop equation, you can probably get something.
So you want to use the next order in 1 over n to bootstrap the zero order. That's what.
Well, yeah, bootstrap together at the same time. Yeah. So you write the like a positivity condition for the double trace operator in the matrix model, and then like a bootstrap simultaneously the leading order and the next leading order. I think that's probably possible.
It sounds counterintuitive to me, but maybe maybe you're right.
Yeah, I agree. I think it's possible. I thought about it, but I didn't implement it. I'm not sure whether it is how to say, whether it is worth it. Yes.
Yeah, well, how well it works, yeah, I don't know, but I think it's possible, and maybe Henry even might have discussed a little bit about that perspective in this paper.
A very nice question. Are there also loop equations in this lattice gauge theories that are simpler than non-abelian gauge theories that one could like
C2 or something? Yeah, there are.
Well, what's the main difference, and so what would be the difference in the bootstrap of those compared to this bootstrap?
You mean something like lattice electrodynamics, or what?
Like what John was describing, the strings for Ising model and so on. Do they also?
Yeah, I don't know if it's a paper by Poliakov or something, but yeah, I think the loops, you have to put the loop split or the cross and the uncross. There is some, I forgot. But there is, you know. And I don't know about the positivity constraints, how that works.
But I guess there's no large N factorization.
That's true.
Okay, good point. Yeah, that's why they cross them.
But there are advantages and disadvantages in it. You have maybe many more loops, but many of them are dependent. Like, by the way, an interesting question is whether we can do something for SU2 or SU3. In principle, one could think of bootstrapping this. Immediately you get many more loops because you have no factorization theorem, but there are relations between these loops also. So it's would be an interesting discussion whether it's feasible.
But John, just a question back to what I was asking. Didn't you exactly introduce some parameters so that there would be some kind of analog of a small G string? Or maybe I'm confusing things. You had a paper, right, where you were deforming Ising so that the effective string has some small G string or something like that?
That was the goal, yeah. Yeah, just explicitly modifying the lattice Ising model so that the worldsheet expansion was more weakly coupled.
So then in that deformation, maybe one could study loop equations and have some kind of large N factorization, the analog.
Maybe, yeah. The problem was though that if we there's a limit to how weak we could make it while preserving the phase transition. So if we make it too big, instead there's some transition to some other crazy lattice scale ordered phase.
Mm-hmm. I see.
Anybody else have any comments or questions or remarks?
Maybe I have a short question. So what is the role of center symmetry in this, especially if we look at this picture that Volodya has with the compact direction, like, and indeed compute the ground state energy, we should see the confinement transition, right? When the circle is small enough. So do you have any vision of how this would happen?
I can comment on that.
Mhm.
So if center symmetry, when you compactify, for example, Yang-Mills theory on T4 or some other QCD on T4, and if the corresponding center symmetry, is not broken as you shrink the, the size of the torus, then there is a concept called large N volume independence or large N reduction or volume independence, or, Eguch-Kavai reduction. So then if this condition, if unbroken center symmetry is satisfied, then it tells you that you can map infinite volume lattice gauge theory to a single point lattice gauge matrix model. So, and there are working versions of this idea. In this sense, center symmetry is very crucial in mapping field theories to matrix models.
May I also comment? Actually, both Martin and Volodya could make their calculations not with unitary matrices, but with adjoint matrices, n squared minus 1 times n squared minus 2. And then there is no center symmetry. But these two latest theories have the same continuum limit. So center symmetry is something which is present on the lattice, but is not present, I think, in the continuum real world. That's my opinion.
But the confinement phase transition is something that's present.
It's
in the
present.
real world, right?
It's present. But
so my question was more about the phase transition, how you would see it in this Bootstrap language.
That's as complicated question as the question of Marek about calculating the correlators. So there is phase transition and temperature, right?
No, why is it as complicated? Here it's enough to have like a single, like one loop, to like expectation value of a single loop will probably tell us whether we're in a confined or deconfined phase, no? Like
but you, as he said, you have to shrink one dimension to make the temperature high.
Yes, because it's temperature phase transition, not on the coupling constant. So that can be started, of course, well, but it's not hasn't started yet.
But yeah, you could put a lattice with a. But okay, you have to put loops that see that there is a periodic dimension which is small, and that should lead to the confining. So this phase at small coupling is confining, although we cannot see it from the small loops we have, but it's the confining phase. If you want to deconfine it, you have to put large temperature.
You mean even if you make this on the picture, make this circle consisting of very few links on the lattice and solve maybe the bootstrap problem, you will not see it. This phase.
Yeah, you may see it, but you need to put large enough loops that go around, I guess.
So you need also other sectors, not only a single winding, you think?
No, Martin, I think there are circumstances in which you can go with the confined phase in the large N theory all the way to one side.
Well, I was really asking about pure Yang-Mills where.
So pure Yang-Mills, for example, you can do one-side reduction in two direction by inserting 2 Hooft flux. That will stabilize the center symmetry in those two directions. In the third direction, third and fourth, do not insert any 2 Hooft flux. Take one of the circle size, shrink it, you will see the confinement transition.
My recollection from the time when I was interested in was that in four-dimensional pure Yang-Mills theory, the confinement for phase transition and temperature was observed for the standard Wilson action with unitary matrices, but it was not observed for adjoint matrices. So for some reason, this calculation turned out to be very difficult, and the continuum limit is not easily likely. So for me, it's still an open question.
So are you asking continuum limit of SUM or ZN theory?
Yes, yes.
Yeah, you can do it. I mean, this was part of the discussion during Davide's talk. So in lattice, it is not what people used in the old times. It is not trace over adjoint. That's not very. There are problems there which are morally similar to fermion doubling problem. If you do that formulation, there are actually extra monopoles, and you don't want them. But there is actually a formulation with link field, phase field, and cube fields, such that you can obtain PSUN theory in the continuum. But I do not know if the loop equations are written for those kind of lattice gauge theories.
Well, you are mentioning some new probably results, which I don't know. But if you just don't speak about loop equations, about these new methods, and you just make thermodynamic calculations for SO3 rather than SU2 matrices on the links. Then I remember 20 years ago, and even before that, there were papers by Philippe Forcran.
Yeah, I know them.
He tried to do that, but my impression was that he was not able to do that due to some numerical limitations. And the question probably you know better, whether this study has been done since that time, recently probably, just the usual thermodynamic calculation.
Yeah, it's not done recently. And also what I am saying is that at the Philippe de Forcran's and others, construction of SO3 theories, there are actually degrees of freedom that are not supposed to be there. This is like well understood in the last 3-4 years, I think.
Okay, so yeah, so I'm thinking maybe we should wrap it up right now. So let's thank Martin and Volodya for a very stimulating discussion.